Hello and welcome to G Fun Facts Online, the show that dives deep into the science behind our world. Today, we're talking about something that can turn a familiar landscape into a scene of utter chaos in just minutes. We're talking about flash floods. When you think of deadly weather, your mind probably jumps to massive tornadoes or powerful hurricanes. But what if I told you that the single leading cause of weather-related deaths in the United States isn't any of those? It's flash floods. These sudden, violent surges of water are born from an incredible interplay of unseen forces high in the atmosphere. They are the furious result of severe thunderstorms, and understanding the science behind them isn't just a fun fact, it's a critical tool for survival. So today, we're going to decode the meteorology of severe storms and unpack the terrifying fury of flash floods. Let's get started. To understand how a simple rain shower can escalate into a life-threatening flood, we first need to look at the anatomy of the storm itself. Think of it like baking a cake, but instead of flour and sugar, you're using atmospheric ingredients to cook up a potential disaster. You need three key things to come together in perfect, potent combination: moisture, instability, and a lifting mechanism. First, let's talk about moisture. This is the fuel for the entire system. You can't have a flood without water, and for torrential rain, you need a tremendous amount of water vapor in the air. Meteorologists look for deep layers of moist air, which are often transported thousands of miles from large bodies of water like the Atlantic Ocean or the Gulf of Mexico. They measure this using things like dew point temperatures and a value called precipitable water, which is basically the total amount of water vapor in a column of air stretching from the ground to the top of the atmosphere. A key scientific principle here is the Clausius-Clapeyron relationship. That sounds complex, but the idea is simple: warmer air can hold more moisture. For every single degree Celsius the temperature rises, the atmosphere can hold about 7% more water vapor. So as our climate warms, the air becomes thirstier, capable of carrying more fuel for these extreme rainfall events. The second ingredient is instability. An unstable atmosphere is one that encourages vertical motion. Imagine a bubble of air near the ground. If this bubble is warmer and more buoyant than the air around it, it will start to rise. In an unstable atmosphere, it won't just rise, it will accelerate upwards, like a hot air balloon with the burner on full blast. This is crucial for creating the towering, deep clouds of a thunderstorm, known as cumulonimbus clouds. Meteorologists measure this potential for explosive upward motion with an index called CAPE, which stands for Convective Available Potential Energy. The higher the CAPE value, the more fuel is available for a thunderstorm's updraft, allowing it to grow to incredible heights and process huge amounts of moisture. A classic setup for this is having warm, humid air near the surface trapped under a layer of much colder, drier air high above. This creates a kind of atmospheric powder keg, just waiting for a spark. And that brings us to our third and final ingredient: a lifting mechanism. This is the trigger, the spark that ignites the powder keg. You can have all the moisture and instability you want, but without something to give that surface air a nudge upwards, nothing will happen. This lift can come from several sources. The most common are weather fronts, the boundaries where different air masses collide. A cold front acts like a wedge, plowing under warmer air and forcing it violently upward. A warm front will gently glide up and over cooler air. Even a stationary front, where two air masses are at a stalemate, can be a focus for rising air. But there are other, more subtle triggers too. An outflow boundary, which is like a mini cold front created by the rain-cooled air from a previous thunderstorm, can trigger new storms. A sea breeze can do it. Even something called a low-level jet stream, a fast-moving river of air just a few thousand feet above the ground, can provide the necessary lift to get the whole process started. When these three ingredients, abundant moisture, high instability, and a strong lifting mechanism, come together, you have the perfect recipe for a severe thunderstorm. capable of producing extreme rainfall. But not all thunderstorms are created equal when it comes to unleashing a deluge. Certain types of storms and weather patterns are especially efficient at causing flash floods. One of the most common culprits, especially in the central and eastern United States, is the mesoscale convective system, or MCS. Don't let the name intimidate you. An MCS is simply a large, organized complex of multiple thunderstorms that work together as a single system. These behemoths can persist for many hours, sometimes overnight, and cover an area the size of an entire state. They are notorious for producing widespread, heavy, and long-lasting rainfall. Then you have the supercell thunderstorm. These are the kings of thunderstorms, often associated with giant hail and violent tornadoes. But they can also be prolific rain producers. A supercell is defined by its rotating updraft, called a mesocyclone. This rotation makes the storm incredibly efficient at pulling in moisture and converting it into precipitation, leading to extremely high rainfall rates in a localized area. Perhaps the most insidious pattern for flash flooding is a phenomenon known as training. Imagine a freight train where each car passes over the same section of track, one after the other. Now, imagine each car is a powerful thunderstorm. When a series of storms repeatedly develops and moves over the exact same area, it's called training. The ground gets hit again and again and again, leading to staggering rainfall totals in just a few hours. This is a classic setup for some of the most catastrophic flash floods. We also can't forget about tropical systems. Hurricanes and tropical storms are masters of collecting moisture from the ocean. As they make landfall and move inland, they can dump truly immense amounts of rain. In fact, inland flooding, not the storm surge or wind, has been responsible for more than half of all deaths from tropical cyclones in the U.S. since the 1970s. Finally, there's a fascinating phenomenon called an atmospheric river. These are literally rivers in the sky, long, narrow plumes of concentrated water vapor that flow from the tropics towards the poles. They can carry as much water as the Mississippi River. When one of these atmospheric rivers slams into a coastline, especially one with mountains, it's forced to rise, cool, and dump its incredible moisture load, resulting in extreme, record-breaking rainfall and flooding. So the storm has unleashed its torrent. But the transition from a heavy downpour to a life-threatening flash flood depends just as much on what's happening on the ground as it does on the sky above. This is the science of hydrology. Several key factors can turn a bad situation into a catastrophe. First is topography. Steep, hilly, or mountainous terrain is a huge accelerator. Water doesn't have time to soak in. It just runs off immediately, funneling into streams and valleys at high speed. This is why narrow canyons can be so deadly. A thunderstorm happening miles away, out of sight on a high plateau, can send a wall of water rushing through a dry creek bed with virtually no warning. Next is the condition of the soil itself. Think of the ground like a sponge. If that sponge is already soaking wet from previous rains, it can't absorb any more water. Runoff will begin almost immediately. The same is true if the soil is naturally rocky or composed of dense clay. Water just can't infiltrate, so it flows over the surface. Urbanization dramatically worsens this problem. Our cities are jungles of impervious surfaces. Concrete and asphalt from buildings, roads, and parking lots act like a giant sheet of glass. Rainwater can't soak in, so the volume and speed of runoff are massively increased. Storm drains, the only outlet for this water, can quickly become overwhelmed or clogged with debris, causing water to back up and flood streets, underpasses, and buildings in the blink of an eye. A particularly dangerous situation arises in areas recently ravaged by wildfires. These areas, known as burn scars, are incredibly susceptible to flash floods and debris flows. The fire destroys all the vegetation that would normally help absorb rainfall. More than that, The intense heat can bake the soil, creating a water-repellent layer, almost like it's been glazed in a kiln. When rain hits this surface, it runs off as if it were on plastic, carrying with it mud, ash, rock, and burnt debris in a thick, fast-moving slurry. Predicting the exact time and place a flash flood will strike is one of the greatest challenges in meteorology. We can often identify that conditions are favorable for heavy rain days in advance, but the thunderstorms that actually trigger the floods are often small-scale and can pop up quickly, making it hard to pinpoint the exact neighborhood at risk until the danger is imminent. Despite these challenges, our ability to see it coming has improved dramatically thanks to technology. The cornerstone of this is the Doppler radar network. Radar allows meteorologists to see inside a storm, estimating rainfall intensity and tracking its movement. Modern radars use something called dual polarization technology, which sends out both horizontal and vertical energy pulses. This gives a much more detailed picture of the size and shape of raindrops, leading to far more accurate rainfall estimates. Satellites are our eyes in the sky, providing a broad view of weather patterns and helping forecasters spot the signatures of developing storms, especially over the ocean or in areas with limited radar coverage. All of this data is fed into sophisticated computer simulations called numerical weather prediction models. These models run on supercomputers and simulate the physics of the atmosphere to predict where severe weather is likely to occur. As computers get faster, these models can run at higher resolutions, allowing them to capture the small-scale features that lead to flash flooding. This atmospheric data is then combined with ground data. A system called flash flood guidance estimates how much rain needs to fall over a specific time period to cause flooding in a particular river basin, taking into account current soil moisture and streamflow levels. All of this science leads to the public alerts we're all familiar with. It's crucial to know what they mean. A flash flood watch means conditions are favorable for flash flooding. This is your time to prepare. Check your emergency kit, review your evacuation plan, and stay informed. A flash flood warning is much more serious. This means a flash flood is either imminent or already happening. This is not the time to prepare. It is the time to act. Move to higher ground immediately. And in the most dire situations, you might hear a flash flood emergency. This is issued for exceedingly rare events when there is a severe threat to human life and catastrophic damage is happening or about to happen. This is a worst-case scenario. The impacts of these events are devastating. The most immediate danger is the force of the water itself. It is deceptively powerful. Just 6 inches of fast-moving water can knock a person off their feet. Just 2 feet of water can float most vehicles, including SUVs and pickups, turning them into helpless rafts. This is why the vast majority of flood-related deaths happen when people attempt to drive through flooded roadways. Beyond the immediate danger to life, floodwaters destroy homes, businesses, and critical infrastructure, like roads, bridges, and power lines, paralyzing communities and costing billions in damages. The psychological trauma of surviving a flood, losing your home and possessions, can last for years. Given how quickly these events unfold, personal preparedness is not just a good idea, it's essential. So, what can you do? Before a flood, the most important thing is to know your risk. Check FEMA's flood maps to see if you live in a flood-prone area. Develop a family evacuation plan, including a designated meeting place on higher ground. And build an emergency kit with essentials like water, non-perishable food, a flashlight, batteries, and a first aid kit. During a flood, the rules are simple but non-negotiable. If you receive a warning or see signs of rising water, move to higher ground immediately. If authorities tell you to evacuate, do it. And please, remember the single most important rule of flood safety: turn around, don't drown. It is never, ever worth the risk to walk, swim, or drive through floodwaters. You cannot see how deep the water is or how fast the current is flowing, and you don't know if the road underneath has been washed away. After the flood has passed, wait for the all clear from authorities before returning home. Be cautious of structural damage, downed power lines, and contaminated water. From the complex dance of moisture and energy high in the atmosphere, to the topography of the land beneath our feet, the science of flash floods is a stark reminder of nature's power. It's a chain reaction that connects a water molecule over a distant ocean to a flooded street in your neighborhood. By understanding these unseen forces, improving our forecasting, and most importantly, embracing a culture of preparedness, we can empower ourselves to weather the storm and reduce the tragic toll of these sudden, powerful, and all too common disasters. Thanks for joining us on Fun Facts Online. Stay safe and stay informed.